All right, we are recording now, just letting you know.
Yay, hard recording.
All right, so
I'm so
Hey,
glad I
everyone.
never made a YouTube channel, actually.
don't
Oh,
forget
we
to
got
hit
500.
subscribe and
It's awesome trick shots.
Like you
click that bell.
I am on a channel. I was featured on a YouTube
I
channel.
was featured on Ryan's YouTube channel.
Dude Perfect.
I
No,
forget.
no,
Dude, Luke had the Dude Perfect phone channel for a while.
Really?
He had like 2 videos where he just did like trick shots with his brothers.
That's awesome.
It was called It's Awesome.
Oh, that's good. That's fantastic. All right, Mod Arg Form. So I'm not going to bore you with the whole unit circle thing, but we do remember that we've got, when we're looking at a complex number, we're looking at the complex plane. So we've got a horizontal and vertical axis. So you've got the real axis and you've got the imaginary axis.
Mm-hmm.
That should give us an idea in the Argan diagram. So you can have a point. Any point on there can be expressed in terms of its real and imaginary parts to give you a complex number. Cool. So in this case, we've got x, y. So that would give you it would give you sort of, what would it actually, I should ask you, what would it give you in complex number terms if you had the point x, y? So x is the real component and y is the imaginary component. So z would equal what? Yep. She's afraid to say it out loud because there's a recording going on and she might be wrong. It is x plus iy. Yeah. So x plus iy. Okay. So now that obviously gives us the standard form that we've been using at the moment. However, there is another way we can do this. And the way we're going to do it based on this is the Mod Arg form, or the modulus and argument of a complex number. So modulus is the distance. So it would be, if you thought about this as a triangle, it would be the hypotenuse of the triangle or the radius of whatever circle you're ending up with. Make sense? Yeah. Paused it, haven't I? Resume. It's coming up on my screen, so we'll record it, and you guys look silly. I don't. So you've basically got a right angle triangle, and the modulus would be the hypotenuse of that. Now, bear in mind that how do we find that hypotenuse? Well, you could use Pythagoras' theorem, but you don't have a length of x. You've only got a length of that little bit of it. How do we find that length? Does anyone remember what these can be expressed as rather than? Okay, so I'm going to assume you said cos theta, sine theta. Yep. So the theta would be that. Do you remember that or not?
Yes.
Because otherwise I'm going to draw a diagram, and we all know how much we like that. Yeah. So we're all right with that. So the x is also known as cos theta. So x can be expressed as cos theta, and y can be expressed as sine theta. Cool. Excellent. So the modulus is just that hypotenuse, and you can see that they've just used Pythagoras' theorem to solve it. If you had the x and had the y, you can actually just work it out. All good with that? Mm-hmm. All right. So the way we write it is like an absolute value.
Is it an absolute value?
Not technically.
Okay, that's great.
Yeah. It's one of them ones.
Not actually an absolute value.
Though, because we are just dealing with a distance, if I said how far is the door away from you, you would give me an answer in the positives, even though it's behind you. So in a way, it is an absolute value because we're only dealing with a length. So we're not talking about direction. So yeah, it ends up being a positive. So, but I just hesitate to say to people absolute value, because then they'll try and treat it like an absolute value, and that's a little different. And then the argument. So the argument of z is theta. Angle from the horizontal goes up, whatever that argument is. So you can then position anywhere around the complex plane just by having the angle that you've rotated around and the distance you've gone from the origin. And that's your Mod Arg form. All right. We all happy with that?
Yeah.
Okay. So like trigonometry, there is what we call a principal argument. Because if you think about it, you can have infinite amounts of theta that would give you the same point. And this is where I start doing the unit circle thing, but I'll also do, if you're talking about a sine wave, it looks like that and it goes on forever. So you can see that point and that point would give you the same, and that point would give you the same. And so you can have an infinite amount of things that are correct. So 30 and 390 are the same. They're in the same spot. Sorry? Yeah. Normally what you do is what we call the principal argument. So between 0 and 360 or between 0 and 2 pi, because we're normally talking in radians. We all good with that? Okay. So most of the time we will go from pi to minus pi. Where's pi? Pi is at 180, so we're talking about here. So normally you're talking about between pi and minus pi. Cool. Excellent. All right. And yeah, we are using radians, and that's pretty cool. Okay. Change pages. All right, Mod Arg. So you've got this. So there is a problem when measuring theta when z is 0 because p coincides with the origin. There's no angle to measure. For this reason, both the argument and the arg0 are undefined. Yeah, that's fine. Okay. Modulus and argument, you've got that box on your sheets. So the modulus of z is the distance, which equals r, which equals o to the point, from the origin to the point. Z squared, or the square of the modulus, is the product of the conjugate and the complex number. Cool. Let's have a look. The principal argument is the unique angle, which is in the range of minus pi to pi. But we don't have arg0.
What is cis?
Sine? Opposite over hypotenuse.
No.
No?
Is that CIS? CIS, yeah.
Ah, cis.
Yes.
We will get to that. We're about to. Okay, so when we're doing this,
Great.
yeah, I know it's great. It is, Mod Arg Form is wonderful. Okay, so when we're doing it, we've already discussed that x equals cos theta and y equals sine theta. Now, as I've said to you guys before, we as mathematicians and teachers lie to you a lot. So I lied to you when I said it's x is cos theta. Okay, that's only when it's the unit circle. Okay, because then what's your radius if it's a unit circle? Yeah, so we keep it simple and we just do that. So it's actually r cos theta, okay, and then r sine theta. That's all. It's just like if you're twice as far out, then it's twice that. Cool. But the cosine of the angle doesn't change. Okay, so that's our definitions. Happy with that? Now, what else do we know? We also know that if you're doing it, you've got the real and the imaginary. Remember, x was the real, y was the imaginary. So if you're thinking about that, then you've got r cos theta plus I sine theta. Yep. So that is the makeup. You've got your real part, which is r cos theta, and you've got your imaginary part, which is I sine theta. All good with that?
Yeah.
All right, cool. So that is the setup. Because now I can take out a common factor. What's common? Excellent. So I've got z equals r times?
Cos theta plus I sine theta.
Yeah, that's a mouthful. Cos theta plus I sine theta. How can we simplify it?
Cis.
Let's simplify it down to cis.
Cos I sine.
Go. So what you've got is you've got r, which is your modulus, theta, which is your argument.
Yep.
And then you've just, that cis is just cos theta plus I sine theta. So it's just a shorthand way of writing cos theta plus I sine theta. Okay. Boom, 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 boom. So what we're going to do is I haven't highlighted anything there, so I'm going to highlight some stuff now. From the trig definitions, r cos theta and r sine theta, which means z equals r cos theta plus r sine theta. We'll take out a common factor, and then we'll just shorten it. And then the bit to get out of that, z equals x plus iy is called real imaginary or Cartesian form. We normally refer to it as Cartesian form, while cis form is the Mod Arg form. So what you'll be doing in this one is you're going to be converting it from Mod Arg to Cartesian and from Cartesian to Mod Arg. that is a very, very useful skill to get used to get comfortable with, so that you can just do it. All right. Now, Mod Arg Form is also called polar form at times because it goes out from the radius from the origin, which acts as a pole, like a North Pole. All right. But no, I don't often use polar form. I think Mod Arg Form's fine. All right. There is some worked examples there. We need to take these complex numbers and put them into Cartesian form. So real, imaginary, and Cartesian are the same. My suggestion for you would be to expand them out into the full sys form until you get used to it. But once you get used to it, they should.
Where's my
Calculator. Now, be aware, and you guys should be all right with this, we are in radians.
Yeah. What do you get for -4? What do you get for heavy? What do you know? No, I got -4.
How'd you get -4?
Because sine of 180 is 0.
Oh, wait, yeah.
So I times sine is
So are you converting it from radians into degrees to do it?
Yeah.
Okay.
Yes.
That's fine. Your calculator can be put into radians. You know that?
Yeah.
Okay, cool. I'm happy with you just being comfortable with however you're doing it. As long as you can do the conversion, that's fine with me. Just be aware that if you get the question asked in radians, you're probably going to have to answer in radians.
Tom, isn't it
Yep.
-4i?
No, because it's I times 0, which is 0.
It's 4 times I times 0.
Yeah, for the sine one.
Mhm.
Yeah, so that's cancelled out. But for the cos one,
It's
There's
-1.
no I in the cos one.
Yeah, it's not I in cos.
Remember, cos is your real component of it.
oh wait,
Yeah, so the cos one is just the real part. The only I is in the imaginary part, which is the y value, which is the sine. So let me know what you got for the second and third one.
√3 plus I.
Yep.
Yes.
See.
what'd you get? What'd you get for beta?
√3 plus 1. You did the same thing as me. I forgot the I as well.
√3 plus I.
Yeah, √3 plus 1.
Now, are you guys writing it out fully as they've done?
Yeah.
Yeah, okay. Especially at the start, I think it's a good idea just to get used to it, get in the habit, or get used to familiar with the way it looks. After a while, you'll probably start skipping that bit.
There's nothing in front of us. It's just
I think for the last one I need my trig identities from extension 1, where it's sine A plus B.
D.
I don't.
For C.
Yeah, the same. Because sine of 120 is a thing, so you have to do 60 plus 30 equals sine of 60 cos 30 plus cos.
Oh, you're remembering your exact ratios?
Yes.
Yeah, okay.
That's not what we're doing.
Yeah.
So you get negative 1 2 plus root 3 over 2i.
So 120 is the equivalent of sine 60.
Also, it would be negative 1 and 2 plus
And
root
the
3,
long
or
way.
I root 3 on 2. Or, yeah, you could write it like that. I'll check that. Yeah, pretty much the same.
Yes.
I just put the I
This
front.
is it. I just put the I up front.
Did you have minus 1 plus root 3i on 2?
Yeah.
Yeah, same animal.
No, you didn't.
I got
Yes, I
negative
did.
half.
That's
Yep,
not
negative a half is good.
It's put it under the same fraction.
So they've
Yeah.
It equals the same
you can
thing.
you can do it where it's all over 2, like because both sides are over 2. So you can have minus 1 plus root 3i on 2, or you can have minus half plus root 3 on 2i. Same animal. Is there a preference for doing either one? The reason they probably, I would assume, have done it in that is because they've kept the real and the imaginary.
That's what I
Separate.
was doing, but then no, I didn't like it.
No, you said you were doing it the other way, and on your page you had it my way.
No, I said that that's what I have because it literally
Every lesson. Seriously, every lesson they're like this.
It's equal.
I can't even go on the top of it. I don't think they haven't.
Well, it is root 3 times I.
No,
It's
well,
it's
you
root
can
3 on
get
2
it
times
times
I. So technically it can. As long as you keep the 1 and the minus 1 that's separate. But they're keeping it so you've got the real and the imaginary separate. All right, so it's pretty straightforward. We've got the hang of that. I think you'd be able to do those day in, day out. Now go the other way.
Oh. Express each complex number in mod.
Oh,
So now what we've got is we've got
wait.
the Cartesian form. We need to change it to Mod Arg. So you've got to, what can be useful here is to give yourself a little bit of a diagram to show you where that point is in relation to pi minus pi, just so you get a bit of an idea of where things are. Okay. So that first one, 5i, well, where is it?
That's a bit.
Up where? It's not up.
Is it? I don't know. I'm actually not.
Well, think about it. What's its real part?
0. So
Okay.
up, like 5 in the y.
So it'll be there.
Yeah.
So it's sitting on the axis there. Okay. So what is the angle?
0.
0. No, 180.
90.
Which is
Pi
also
on
known
2.
as
Fine.
pi on 2. So you're starting to get, so you've already got the argument, and what's the modulus? Distance.
5.
So 5 cis pi on 2. So you've got the modulus, cis, argument. And then-
getting there very slowly.
That's all right. That's why we practice. Then the next one's 3 minus 3i. So where is it on the where is it on the imaginary? Where is it on the real? Think about what that angle would be. It would be because it's gone out the same amount as it's gone up. So but you've also got to look at which quadrant it's in. Not that it matters, but
Do you have to look at what quadrant?
so remember, pi is there, minus pi is there. So you're going in between them.
What?
Well, we're doing it
Oh,
for
it's
angles
negative
between
45.
pi and minus pi. So that 3 minus 3i, which quadrant's it in?
The fourth one.
Okay. And you said it was 45 degrees?
Negative.
Yeah.
So it's negative 45 degrees or negative pi on 4. Cool, because it's down here.
What happens if they're not nice numbers?
They are nice numbers.
Yeah, but what would happen if they weren't?
They'll give you one like question C. Give it correct to 2 decimal places. If they don't tell you it's going to be in decimal places, it's probably going to be the exact values or combinations thereof. Now, you've already worked out the argument for B, but have you worked out the modulus?
3 root 2.
Cool.
So are we just using trig to find like the angle and the length? Is that what we're doing?
Using trig to find the angle and Pythagoras to find the modulus. Isn't it depressing when your year 7 and 8 maths comes in handy? But I was talking to my year 8s yesterday about this. Like, they're doing Pythagoras and linear relationships at the moment. I'm like, guys, my extension 2 guys are using Pythagoras at the moment as well. It does actually help.
Wait, did you say it was 3 on root 2?
Yep.
Oh,
No.
No.
Root 2.
So you'll notice with some of these, the argument is easy to find. Like, you look at it and you go, I know what the argument's going to be. So when you had the 3 and the 3 in there, you kind of knew that it was going to be a 45 degree or pi on 4. You just had to know which quadrant.
The 36.87, the angle for C.
For which one, sorry?
C.
No.
What's that? What is it?
Minus 2. Oh, hang on. You're talking, you're doing degrees, aren't you?
Yes, in degrees. Would we have
Should I
to?
change it back?
Yeah, change it to radians, see what you get.
I don't even. How do you change it for rate? I actually forgot.
You do times 1
No.
well, pi
Yeah,
by
I
1.
tried to. Yeah, but you can't. It's not a whole number, so it's not going to work nicely with that conversion. So I want to change my calculator to radians.
Oh, I wanna do that.
And I like you forgot how to do that. It's in settings.
Oh, wait.
Wait, no.
If it would let me go.
This triangle.
2 settings. Angle unit.
There's my right angle. Sure.
Okay.
What's the answer?
Minus 2.5.
2.5.
What do you get for your arg?
I got.
Say that nicely. What do you want?
What do you get for the angle?
Oh, I don't know yet.
I did.
I got.
Okay, so it's a triangle, right?
It is. It is.
And it's got 3 and 4,
Which means the hypotenuse is
5.
good.
And then to find the angle, you do 10, 3 or 4.
You could do 10.
Is it 4 or 3 or 3 or 4?
I did
Square
sine
is
minus
3
1,
over
3 and 5.
What does your triangle look like?
I
Isn't it
got
this one?
0.64.
Are we finding here?
Yeah.
And then we're doing that minus that.
So you got tan of 3 on 5, did you? Sorry, 3 on 4.
Triangle
Yeah.
the wrong way the first
Yeah.
All right. And is it positive 3 on 4 or is it minus 3 on 4?
Well, they're both negatives.
Yeah, they'd be both.
So
Okay. What'd you get?
Well, it's in degrees, which is 36 point.
Which is 0.64 radians.
Yeah.
If I put my calculator. to
Okay.
radians.
Let's have a look at it for a sec.
Why do you have
3 and 5.
sine?
Because I use a hypotenuse.
So you used sine.
Okay.
The question here, they've used cosine.
So that it would be 4.
Okay. So, all right. But before you do anything else, what have you just found? Now, you said there's a triangle.
Yep.
Is that the triangle that you got?
Yep.
Okay. So what did you find?
The angle, like at the center.
That angle there, right?
Yeah.
Yeah.
Okay. But what angle do we actually want?
Oh, you want the whole.
We want
That's
that
what I said,
angle.
and you went,
I wasn't.
what?
I wasn't listening.
You were saying that, and I'm like, what?
I drew my triangle wrong the first
Oh,
time.
it must be above the horizon.
Oh, sorry. I've just drawn too far. Too far. Boom. There. It's better. I'm only going there.
So
The other way you can do it, just so you're aware, because we're going around to minus pi, that angle there is minus pi plus that angle there. Does that make sense?
Yes.
Mm.
So this angle, like this is minus pi if it went all the way round. So minus pi, and then you add that bit back on, it'll bring you back.
Yeah.
Is that okay?
Yeah, sure.
So if it was 45 degrees, for instance, then that would be pi on 4. So if you did minus pi plus pi on 4, you'd end up at minus 3 pi on 4. I can't remember. Can't count.
Wait, so was the answer 2.49?
Yep.
2.5?
Yep. So that's the radians. That's the argument.
Cool.
I forgot how to use
Did you get 36 points something?
I don't know what I'm doing. That's the issue.
Oh,
Anyway. give me a second.
jeez. I'll just kick back and relax for a while. Then.
Okay.
I appreciate the fact that you want to sort it out yourself.
So, I was doing the homework like all week, and I was stuck on question 7 the whole time
Yeah.
because it says I was doing 1B, right? And it says solve these. It gives you quadratic equations.
Yes.
It says solve them using the method outlined in box 11. And box 11 is the z squared minus 2 real alpha z plus alpha times conjugate of alpha equals 0.
Yes. Yep.
And I don't know how you use that to solve the quadratic equation.
Okay. Which one was it?
Like question 7a on exercise 1b, I was doing.
All right. Cool. Well, what we'll do.
Because I can do it not using that.
Okay.
I don't know how you use it.
Yeah. All right. So we're done with those worked examples. Happy with that.